Thank you, Nick, for the intro. Thank you very much, Philip, for the invitation to do this lecture. So, as you can see on the screen, so it's going to be about multi-materials, and I'm going to explain what these are throughout the lecture. And the way this has been structured is through research project that I've been working on over the past years. And the idea being that they all explore this idea of multi-materiality through various design research projects. So in terms of my background and what I do currently, this is work from the Bartlett, where I'm associate professor in architecture, co-director of the Architecture and Mars Part 2 program. And I also do research on multi-materials at the sides. In parallel to that, I have this small practice called Continuum Design and Architecture that we do some research projects, and we also do building projects like the one I'm going to talk about very soon. And yeah, I mean, the main research focuses on multi-materials and also on, more recently, on topology optimization. And both of these things, topics, is something that we're looking at in the workshop here in DigitalFUTURES as well. So in terms of the first part of the lecture, buildings, I will talk briefly about this building that we completed called Kozhou Tourist Center. And this is in China. So it's in this small village that is 4 hours southwest of Shanghai. And it's in the outskirts of Huangshan Mountain. And it is in this very scenic location, which is quite remote. And the whole idea there and the brief for this building was to design and construct a tourist information center. So there are a lot of people that visit this remote area. And the village wanted to create more like a focal point for these visitors and also to be able to buy local craft, etc. So we started the design by looking into a basic geometry like this. And for some reason, I was thinking afterwards, whenever one starts a design, they always have this very Platonic Cartesian type of shapes in mind. But the problem, if you put a block there, is that it blocks like the passage from one side of the side to the other, the canal that is right next to it. Of course, it also blocks longitudinal movement as well. And the roofscape becomes completely unusable. You can't do anything with it, and therefore, it's almost like it doesn't exist. So in terms of the processes and the things that we wanted to do, number one, we wanted to open up an opening for the entrance into the center, but also to allow people through and to the other side. And then the other thing that was a big inspiration, this was from the El Croquis magazine back in the mid-90s when I was kind of a teenager getting into architecture. This was dedicated to Zaha Hadid, early projects. And she was talking very much about the idea of the landscape as a plan at the time. So this is a project in Germany that they materialized. And the whole idea is that it's made out of concrete. But the main thing is that you can see the paintings, the early paintings by Zaha on the left, is that it merges into the ground and it allows this movement through and across and over it as well. So the way we wanted to achieve that was to put 2 staircases on either side of the building, a more kind of formal one on the south and then a short and a smaller one on the other side, in order to also enable movement on the roof and allow people to be able to see views of the landscape, etc. So with that in mind, the other main thing was we did these studies, and when you leave the facade uncovered, like just with glazing, it creates quite a lot of strong light in there, which would become quite visually difficult for people inhabiting. So the moment when you start to put louvers, it reduces this quite a lot, the daylight factor and daylight hours that are kind of outside the range, and therefore it creates a much more comfortable environment. So that was the main idea in terms of the facade. And from that point onwards, we started to explore and look into possibilities in how we organize and structure these ribs. Also, there was this idea of planting, etc. So what we came up with in the end was to use these curve attractors in order to be able to get the ribs to swell, to pronounce the entrance to the building. And also the idea, the lower part, was to be able to accommodate these horizontal pieces of timber that would be inserted to allow people to sit there. So in that way, we also kind of activate the facade and it becomes more than something that you look at, but it invites sitting as well. The problem, however, was that when you design these curves, if you put a lot of, the higher amount of control points you put, of course, the longer it takes to cut. And the people in the village, or the village workshop, it does have only basic machinery. So it doesn't have CNC kind of machines or laser cutters or anything like that. So we did this study to see how much can we reduce the control points in order to still preserve the legibility, but at the same time allow easy fabrication. So in the end, we ended up with a profile like that, so quite easy. You have a piece of timber, you draw a dimension down, one across, you mark the profile, and then you cut it manually. So that was the plan at the center. On the left-hand side is a craft display area. On the right-hand side is staff offices and toilets. And these were all the unrolled ribs, flat, and how they correspond to the facade. At the south and north side, they follow the inclination of the staircase, and then these were the instructions that were given to the people at the village. They cut them down by hand. The other thing here that was quite important was to be able to realize this building. You cannot really build anything that is outside the standards and the characteristics of the buildings of that location and that area. They all need to be white, and they all need to have like pitched roofs, basically. And the reason why we managed to do this was because this had no foundations, and they had to build this slab at the bottom also because it floods from the river that is adjacent to it, and therefore they had to raise the building up. The frame was made out of steel that was kind of quite local, and then all of the timbers were laid on the sides. They were fixed on the facade using these little kind of like black tabs that you see. And in terms of how these were coordinated, so the column grid was every 3 meters, the facade paneling grid was at 900 and 1200, and the ribs were at 300 centers, so everything, all of these different layers of the building were aligned together to be able to create kind of like easy views out. That was the design that we came up with at the end also. And the other thing the other idea that we had, this was something that I developed back in my DRL days 20 years ago, using Fry Otto's like a principle of like the web threads that you can actually achieve computationally these days. And the idea was that the ribs would be very linearly organized on the facade, but inside they would break down into this much more complex pattern at the ceiling to animate the ceiling. So this was the idea of the interior, basically, of how we would actually design it and fabricate it all by cutting these ribs. And that was what was built in the end. Obviously, big difference. Actually, they built quite a lot of buildings there, and I was told by the client that this was the most expensive one because they also had to hand cut everything. So therefore, they had to do a lot of like savings in the interior. But nevertheless, the design was very close to, the outcome was very close to the design. You can see how the kind of these ribs swell out in the facade in the entrance to mark the entrance. There was also this quite interesting play with the trees that were adjacent to it. They somehow kind of like mimic the profiles. And when you would see the building from the side, it would become quite like hermetic and like almost like a closed object. But straight across it, you would be able to see through it. It would kind of dematerialize quite a lot. So this would be the view from the north, looking at the smaller staircase. And then this would be the view from across the river, again looking from north downwards towards the south. So another small project that was also featured in the book that I published, that I'm going to show afterwards, was called the New Z Canopy, and we wanted to look into plastic fabrication and 3D printing. The idea being that we wanted to create this enclosure and canopy by 3D printing like a plastic lattice using different types of like plastics from transparent to more opaque. So this is work that a student of mine did at the AD program at the Bartlett. And what we very quickly realized was that it takes an enormous amount of time using the equipment that we had at the Bartlett to be able to fabricate this. So we came up with this technique that you see here, where we have a roll, basically, fixed on a CNC machine that goes backwards and forwards. It rotates, and while it's rotating, the extruder is depositing plastic on it, and that way you can create these very large sections where you can also vary the density of the plastic as well. So we're able to play with all sorts of different like patterns and densities. And in the end, yeah, I mean, we stacked all of these together. This was a very short project. I mean, if I had more time, we would have kind of made these larger, more continuous, etc. And as part of that, we also studied how the density and the patterning of the section and each one of these rolls affects how much they start to deform. And obviously, like if you have a very sparse pattern, what will happen is they would kind of like, you know, bend quite a lot. And the idea was simple, a saddle-shaped like geometry, where you have more curvature, it becomes more sparse, then it becomes more dense at the end. And that was the result that was installed in Guan's facility in Grimsdijk Farm. So these were kind of larger scale projects. And this goes much more into kind of like specifics about the research that I'm doing with carbon, with topology optimization, etc. So there are two big things here that affected all of this research, and like I used to kind of like argue for my PhD that I finished 8 years ago. So number one is the manufacturing scale is increasing. At the time when I was doing my PhD, we're looking at relatively smaller scales, but now we can see even whole buildings being 3D printed. And what is happening in parallel is like this is like a little hinge that is used in aircrafts in the aerospace industry. They used to bolt the two parts of the hinge together and also weld them. This was very chunky, heavy, and it would take a lot of labor, obviously, to manufacture it. Using topology optimization and 3D printing in titanium, you can reduce the weight of these, reduce the cost, reduce the weight of the aircraft, and reduce the carbon dioxide that is being emitted because it's a lighter aircraft. And yeah, I mean, there's ongoing research. This one is by the European Space Agency looking into 3D printing whole structures of satellites, which is something that would save millions of euros and 50% of the cost. Also Foster with Skanska having looked at 3D printing building components and also using this hybrid additive subtractive process as well. And yeah, I mean, there's also these scaled up kind of like manifestations of this. This is Wingsun actually here in Shanghai that were 3D printing whole buildings at the time. And this is Bjarke Ingels in Texas, in Austin, I think, that they are actually 3D printing these now. It's a whole master plan of 3D printed houses. So the first project that somehow starts to relate with all of these is called Topologically Optimized Metal Building Components, funded by UCL. And we're looking at this good old kind of humble bracket that is being used to hang curtain wall paneling on the facade of the building. This at Tottenham Court Road corner and Oxford Street in London. And yeah, as I mentioned, they connect cladding to slab. And when you start looking at the engineering of all of this, is very, very over-specified. So they use much more material than is needed. More material is heavier, is costlier, is more carbon kind of intensive, etc. So what we did here is to use this technique again called topology optimization, where you fix these brackets, you put loads, and then the computer works out the optimal material distribution. We did this with all sorts of different constraints. And also these then were the results from the computer. For some weird reason, although we loaded it symmetrically, the result was asymmetrical. And these were some of the results, again, with partial z-axis constraints, also thickness constraints, etc. So the big problem here is that in the computer you can do this quite easily, but the question is how do you manufacture this, because it's more complex as a geometry. So we looked into casting. You 3D print a sand mold and then you cast metal inside. But these blue areas that you see there is where the metal will get stuck, and therefore you won't really be able to do it like that. So in the end we followed more standard techniques. So this is metal 3D printing, stainless steel, other are bronze and steel as well, and then there's other ones that are S275 steel that is milled as well. And then from that point we did them all in couples, so duplicates, one for horizontal load testing, the other for vertical. We put these, so this is a collaboration between us and the technical university in Lübeck. So they fixed these and they put a lot of force, pressure downwards and outwards to simulate the wind loads. And the long story short, and what these diagrams show, is that the optimized facade works very similarly to the full mass equivalent. And then another part of this research was quite interesting. This was done by material scientists. When you 3D print something using powder bed fusion, when this cools down, there's residual stresses being developed within the material, and that makes it kind of behave differently to what you predict. So these scientists did some little holes in there and measured the residual stresses. So then the other big story with this was carbon. How does this compare carbon-wise with the full bracket? We looked at the data of the printer. We worked out from here the kilowatt-hour consumption to 3D print this. And from that, you can very easily work out the carbon dioxide. So this is how they compare. Obviously, I mean, the more complex one has 15 kilograms of carbon dioxide equivalent. And yeah, I mean, the standard one, 9, but the one that has a smaller mass but is a straight cut has only half of that. Of course, when you do a straight cut like that in a quite a weird shape, these are all cut in big kind of like machines like that, you will have a lot of offcuts, and that's another thing of what you do with the offcuts. But then the story for me gets even more interesting, because this is very high here, the carbon, because you use a lot of electricity for 3D printing. But the thing with electricity is that if you look at the makeup of it, it's made up of fossil fuels, renewables, and other sources. But it depends on when do you 3D print during the day. So if you 3D print at night, for example, the makeup is different. Or if you 3D print on the weekend, it's different to a weekday as well. So you can see the difference between the 7th of May and the whole period across a month. The other quite weird thing with this is that renewables, when we say renewables, is wind energy, solar energy, and biomass as well. But biomass is kind of created in places like that. This is the Drax power plant in the north of the UK. It used to burn a lot of carbon, but because the UK wants to switch to renewables, it's burning biomass. Biomass is considered renewable, but apparently it is even worse than carbon. It releases even carbon dioxide than actual coal itself. And the decision to consider it as renewable was made long before the time frame set out by the Paris Agreement began. And it was a blind spot in the Kyoto Protocol dating back to '97. And this loophole effectively allows you to create lots of very carbon-intensive energy, claiming that you're bringing down emissions, which is kind of a complete paradox and contradiction. So in there's a lot of stuff that is kind of contradictory, and you know, like it's a bit of a rabbit hole to investigate even further. So all of this work has been captured in an article that we published in the Architectural Intelligence Journal that analyzes all of these things in more detail that I mentioned. And then the other big thing that you know, was quite key to what I was doing is that the scale of manufacturing is increasing, but also the materials you incorporate are diversifying as well. So I always show this slide that the space shuttle is using composite panels. And however, these composite panels have a completely different makeup depending on where they are to correspond to more higher temperatures or higher loads, etc. So this here gets into a lot of detail, but inside the satellite is something very interesting as well. There are carbon fiber panels fixed to a metal frame. Carbon fiber has a different expansion coefficient to the metal frame, and they would tend to fall off the frame because they expand differently. So the way scientists resolved that was to create a multi-material insert in between that has part the thermal expansion coefficient of carbon and part of steel, and therefore this takes up the difference very nicely. So in terms of the different materials, that this is something I had to use for my PhD as well, in terms of classifying what they are and showing what I'm interested in. I'm interested in number 8, functionally graded materials that look like something like this. So this is a photograph of one. On the left is what is called zirconia. Zirconia is a ceramic. On the right is stainless steel. So this is ceramic fusing into stainless steel in one continuous condition without mechanical connections. So you have the 3 types of materials: alloys on the left, composites in the middle, and multi-materials on the right, and this is what I'm kind of been working on all of these years. And this is something they've been doing in researches in Germany. Michael Herrmann I've been collaborating with for years, looking into graded concrete. And the whole kind of let's say argument or hypothesis, this is how buildings are constructed. You need, even to make a window detail, you need all of these different layers. It's a very messy, conflicting, kind of convoluted process. We are in this slightly kind of more awkward stage where parts of buildings are 3D printed, but still conventional windows are fitted out. And where this research is operated more is in this kind of hypothetical, speculative scenario where everything is fused together. There's no joints, no glues, no bolts. Everything is continuous. So as part of my PhD, I started to also do these point syntax, basically, describing the changes that will come about because of these materials. For example, discrete boundaries will be replaced by gradients. The acceptable margin for error will increase because gradients are more forgiving than components. And also, you will not longer need to translate 3D information into drawings and back into 3D space. It would be a much more immediate design to fabrication process. So this here then goes back to optimization, but here we're starting to use more metals in there. So we take the good old humble I-beam. The I-beam, again, I mean, it uses far too much material and much longer than, much heavier than is needed. So what we wanted to do, first of all, is to look at the materials that can be 3D printed. This is from Meltio in Spain, a company that we collaborated with in this project, and Foster and partners were involved as well. And we looked at basically the standard steel that is used at the bottom, S235, and how that compares to 3D printable metals like mild steel and tool steel. Tool steel is, like you can see here, the yield strength is like 5 times higher than standard steel used in construction. And therefore, you can use much less of it to create a beam. And you can also combine this with mild steel in areas that take less loads to create a multi-metal beam. So the standard one is at the top, the single material one at the center, and then multi-material at the bottom. There's a lot of research in there, but the long story short is that each one of these types of steel has ingredients within it, like iron, carbon, manganese, chromium, nickel, etc. And each one of these contribute to its embodied carbon. And therefore, in the end, this is what you get when you start to calculate these. Mild steel and tool steel are very similar to standard steel used. But of course, because you reduce the mass, you can also minimize the carbon as well. So we started with the optimizations, and one thing that this is in 30% volume fraction. So this is 30%, 70% less of the original beam. But of course, you can start to increase volume fraction, so the way to 100%. You can mix different materials together, different types of metal. And also, I mean, what we found out, however, is that if we take 30% volume category, not all of these work because engineering-wise, the tool steel should be at the top part and then the mild steel at the bottom part that does less work. So we eliminated quite of these options. We simulated its displacement in the computer. We eliminated then even more. And in the end, we came up with this little band of beams that are actually usable. So Meltio, the 3D printed a standard beam vertically. I mean, this is quite a simple extrusion, like you just do it upwards. And this is the result. Something quite interesting here is the more energy they use, the more the metal coagulates. So you can see the difference here at the top in the middle. It has these little black spots, and this is where the metal hasn't stuck together properly. And then the other big problem with when you use more complex geometries is that they can't really 3D print these without supports. And not only that, so the colors that you see on the left vertically, they are all different toolpath orientations. So the robot needs to change every time. And when you have the symmetry axis, because each side is printed differently, it won't behave the same structurally. So we had to use a lot of supports. this is like what the robot does basically. So this is quite like a chunky type of piece of metal that comes out like that. The supports were removed, and then this was the final result. So we had single material beams, dual material, and then we tested these as well. The other interesting thing is that what you can also start to do computationally, design-wise, you can start to zoom in even more in there and remove more material and correspond this also to the loads in the beam. So this is how you can start to create like perforation gradients following loading conditions as well. And also at the moment here, this was only focused on mild steel, but you can get that on both types of steel as well. And Melgio, the did tell us they can 3D print gyroids, so this is feasible as well. We haven't done that yet, however. And then lastly here, I mean, the beam that we printed was quite, I mean, it was 50% lower in terms of mass. We wanted to push this even more. And we did this in MX3D in Holland. So what happens here is like they're using multiple axes, basically. So there's a base that rotates like a XYZ, and the robot can rotate. And by doing that and keep rotating this, what happens at the end is they are able to print this without any supports. And then you can see the result at the end here. So they printed 3 of these, the idea being to be able to test these. So that was the result here. I mean, there are quite interesting textures here, but this had a lot of problems. It took a very long time, and it was much thinner than we wanted to do, so this is something that we need to revisit. So this one here is another project that feeds into some of these themes. And so Google, the search engine, they also have an R&D division, and they do a lot of research which they don't really publish. And as part of that, they kind of opened this fellowship. I applied, and I was one of the 4 fellows selected to do research on facades and envelopes, looking into embodied carbon. So again, to be able to make a window detail like this is very carbon intensive. Like even something like this carries like 27 kilograms of carbon dioxide. So the interesting thing, however, is when I visited San Francisco and Palo Alto at the Googleplex as part of the fellowship, they were building this building in collaboration with Excel Construction, another company there. And I spoke to the construction manager, and the quite kind of crazy thing that he said was that the paneling there, the raw aluminum is extracted in Vietnam and goes to the East Coast in America. That is converted into mullions. The mullions are shipped to Thailand. The glass is made in Germany, also shipped to Thailand. The panel is assembled in Thailand and then sent over to San Francisco for installation in the building. Of course, I mean, this is 52,000 nautical miles traveled across the earth to be able to make the facade of one building, which is kind of incredible if you think about it. So, yeah, I mean, for 500 panels I worked out, that's almost like 500 tons of carbon dioxide, which is very high. And all of this is happening because the factory worker salary in the US before tax is quite high. In Thailand is much lower, so financially it makes much more sense to do this in Thailand than in the US. So yeah, I mean, this is another project that after you do all of this process, you end up with something like this. This is a thermal image that we took of one of the UCL buildings. The building just leaks out heat and energy because the aluminum is a very good thermal conductor. And the loads that are acting upon it are heterogeneous, of course, structural loads, wind loads, slab deflections. So what this goes back to my PhD, wanted to do is how can we eliminate all of this, manufacture this in one go, eliminate connections, reduce embodied carbon. When you want to work with multi-materials, we discussed this in the workshop here. This is what we work with in Rhino, boundary representations that are boxes without materiality. So if you want to engage with multi-materials, there are voxel-based techniques like monolith, and also particle system elements like this one here that my students did. So I was trying to, like in a very crude way, start to mix materials in the beginning. The materials were mixing computationally. I managed to do this at the end, again, this is all quite crude. And the other thing is, like, very often things we do in the computer, they have no correspondence to reality, and this is very easy trap to fall into. So what I wanted to do is to make sure that whatever I design in the computer also connects to what's happening outside the computer and is verified. So these are material science studies of glass fusing with ceramic and metal fusing with ceramic. So in principle, you could design a graded material of glass fused with ceramic, fused with metal. So that was kind of like a small simulation that I did of that detail. And that was the result of this like study of how you can design that little detail through a multi-material. Again, this is easy. I mean, not that easy, but kind of you can do this fairly straightforward way in the computer. But how do you manufacture it is another story. So we did kind of go for it, seeing could this ever be possible. So use aluminum powder to melt it in between molten glass and see would that create a graded material. Of course it didn't, and this was the result. So this was metal on the left, glass on the right. This was full of bubbles and trapped air. The metal didn't really fuse with the glass, but it was a very kind of rudimentary, let's say, basic way for us to start to explore the idea. And then another thing here, I'm missing the video here, is this research fed back into the student work as well, where we try to topologically optimize large pieces of glass and sandwich metal powder in between to fuse it together and increase its structural capacity. And these were the results of the work. So these are full glass panels there, and with metal, actually all these colors that you see is metal powder that has been heated up and has been fused together with the glass. So then this jumps into another study of how do we actually multi-material print this directly. So this gets into a lot of detail. I will make it, actually, I won't go into detail, but you cannot really do this from RealFlow, the software that I use to do multi-material design into Rhino, into 3D printing, because you cannot export the material information from one software to the other. So I had to write all of the material information as an Excel file with RGB values. It's not really material, it's color values, but these are translated into materials to be able to create this correspondence between the two. Doing that is very complicated because this mesh has hundreds of thousands of vertices. Each vertex carries RGB information that you can see here. So you have 6 particle systems at the top. Each one has an influence on the vertex, and the color of the vertex has a different ratio, percentage of influence. So when you do this, you end up with a file like this that is 3.5 million words. It took 5 minutes to open. Essentially, you can't use it. I managed to reduce it down, still very heavy. We tried all sorts of different things in terms of data translation. How do you subdivide, like add together the RGB values and average them out? None of these work. And in the end, I consulted with Next Limit Technologies that write the software. They wrote a simple Python script. It was 900,000 words. And then I took these values, applied them onto the vertices, and then that was the result. Initially, it was a sandstone 3D print, one material but different colors, and this is the detail. But then it becomes slightly more complicated when you want to use polyjet materials. There is a way to unwrap the textures into a flat map and put it back in the model when you 3D print. But in my case, what I did is I converted the gradients into discrete layers, and each of these layers corresponds to a material in the printer. So that was the detail after it has been discretized into, and these are the different colors. This is the exploded that shows each multi-material. But in the end, this was what was 3D printed, only 3 out of how many materials. And the reason for that is because when you offset the mesh, it starts to intersect. That cancels the materials out. You can see here actually this model, I mean, it's supposed to be only a little detail of a panel. And you can see how complex it gets and all of these intersections in there. And yeah, I mean, it's not very easy to work with this. So the long story short is that in principle, using these materials, in this case, going from flexible to rigid, from opaque to transparent, you can start to design these kind of continuous envelopes. You can take into account load criteria, solar radiation, aesthetic criteria, and be able to customize every single part of the facade using 3D printing on site. You cancel out this process completely, and obviously you reduce carbon and complexity. This was a bit sci-fi at the time. This is not so sci-fi today, I think, because this is kind of panels that Professor Mungenas has done in Munich, where this is a prototype for like cladding the whole BMW temporary museum in Munich. It didn't happen in the end, but it's perfectly doable. And then from that, we started to scale up. This is work that I've done with Sam here, where we looked at TWA designs, Mike Davis, polyvinyl wall. This is back from the 80s. And the idea was, how do we apply this across the whole facade? So we got the geometry, we designed the colors based on solar radiation analysis. We unwrapped the kind of material information as a flat map. We did other studies of how we can put a reinforcing pattern there. And this is kind of like the whole process. So we topologically optimize. Actually, this is very similar to what we want to do in this workshop here. We optimize the pattern here, the idea being that this becomes like a reinforcement of the facade to reduce displacement. We start to remove more material where loads are lower. And then there's this solar radiation analysis here that we take in order to convert into transparency and color values as well. So the top part is supposed to kind of face obviously the sun directly, and it's more opaque or completely opaque. The parts that don't have direct light, they become more transparent. There's this network of electrical circuits, and then this is the whole design at the end. This was the 3D print, still very expensive when it's relatively smaller scale. It's still kind of, it's in the hundreds of pounds type of category. But we continue this research because the design of this was quite arbitrary, the envelope design, and we wanted to be much more specific and controlled in how we went on about this. So in this process here, what we wanted to do was to form find, optimize, and then convert this into material information for 3D printing. The idea being that we had three objectives: reduce summer solar radiation, maximize solar gain in the winter, and minimize structural displacement. These criteria are very conflicting. So we use this Pareto front algorithm. Fadi used it that we worked with. This produced, I think, 1 billion options of the algorithm trying to meet this criteria. We reduced it down to 16 options, and then from there we got one. And then from there, a very similar process of structural analysis, topology optimization. You can see what the optimization does in terms of displacement, that the one on the far end, it has both optimization on the inside and outside, and that reduces or minimizes displacement. Reduce material as well, and then the other big kind of idea was that we would have these voids in the facade to be able to allow air circulation. This software also allows for fluid simulation and flow simulation, so you can see them here. We were trying to get equal velocity across the whole void system. And then we take this information out from one software. We convert this into Houdini, into this color and material information. These were the renders here, and then there's another big thing about how do you kind of start to slice this that Sam did, where we convert this into a voxel model. Voxel kind of contains material and alpha values. But as you can see here, even a small detail of the gradient there is converted into little pixels, and each of these pixels corresponds to a sub-material in the polyjet printing. And choosing more materials on the left here, 4 versus 3, you get very different optical results as well. So this is another kind of, in a way, rabbit hole to get into, to be able to control the number of materials and its correspondence to transparency. So the 3D print that was kind of output from this was this one here, fairly small as well. And then afterwards, what we've been trying to do is to scale up. So this one-to-one detail of what you just saw. This is another thing that has many other complexities. Like when it's empty, of course, it's not structural. We put a gyroid in there to fill it in. But then we are trying to also test at the environmental chamber in UCL to see the impact of the gyroid or of the air on how much heat goes through this. So the chamber has a wall, one side is 0 degrees, the other is 20 degrees, and you can study the heat flux. And yeah, I mean, how do you actually achieve color gradation? This was done in Taiwan basically by a former student of mine. If you make the extrusion be faster, then you can make the material more transparent. And I believe this is the final project here where this has been scaled up into a house. The whole idea is that, I mean, I used to call it House of Transitions, with a bit of a funny name, but the idea is that, again, you never go from one space into the other, and you have this idea of gradation from in between spaces as well. So what we want to do, this with Sam, again, we want to get in much more detail into controlling the materiality. So we started to create these lattice-like geometries that would be part of the envelope. And again, following a similar process of gradation from bottom to top to control transparency, then some solar analysis and load analysis. And then these feed into kind of like almost like veins into the envelope that control light and also act as a reinforcement patterns as well. And the idea is, again, that this is kind of all one thing. There's no kind of connections. Of course, this is not feasible at the moment, but this is more like a speculative kind of scenario of what we may end up with in architecture in the future. And these are more kind of close-up renders of, I mean, it's supposed to be a house, and you can kind of circulate from one space into the other more continuously. And when you start to look into this, it has all sorts of different spatial, material, privacy, and other like types of gradients and transitions, basically. Yeah. So, yeah, I don't know how long. It's almost like 40 minutes now. I think I'm going to leave it at that. Or should I? Maybe I'll just play this quickly. So this is for 5 minutes. Is a student project that was in my cluster, RC8 at the Bartlett. The idea was, again, to use multi-materials to design with. That was a new canopy for Euston Station right next to the Bartlett, because the idea was for them to be able to work with this multi-material brick, basically, that would be brick powder fused together with glass powder to create compressive structures to cover the whole station. So I think if it's okay, this 5 minutes, I believe I'll let it play. We can. So there's another project, I'm not going to show it. All of this information that I showed was like part of this symposium that I did at the A. It's been like 8 or 9 years now, but you can find it on YouTube, I believe. There's this book that is almost like the proceedings of that symposium that I edited. Different writers have been, and designers have been writing about multimateriality. And lastly, this book was published last year. It's partly authored, partly edited. It has some of this work that I showed, work from my PhD and also work from other institutions on 3D printing. And of course, I mean, we did this special issue on multi-material design and fabrication of the Architectural Intelligence Journal, and now we have around 8 or 9 articles there. There's a couple outstanding, and then we're done with that. You can find both of these through these links. And yeah, I'm going to leave it at that. Thank you very much for watching.